So in the XZ plane, this will be a circle. Wow. So why do you think I just left this like this then, possibly? Especially considering what this looks like. Yeah, I'm going to convert that to polar. And the exceptionally funny thing about this problem is, this is sort of semi-cylindrical coordinates. Right? So it's yes? Well, I say it that way because we typically consider z to be the height, but to be honest, it truly is totally cylindrical because it doesn't really matter what I call y, x, or z. It gives a shit. But normally we consider z to be the height, and then x and y we convert into their polar equivalents. So it's like polar, and then allow it to move in the z direction. But we don't even have to think about this like this. What goes? All right, let's see. What does y do? We just said that a minute ago. Well, let's start with. Let's just leave this alone. This is going to be this region here. So we're going to worry about that in a minute because I can convert that to polar. Which is another reason why I want to do it this way, because everything kind of falls into place for polar coordinates. What is this? What's y going to do? Yeah, go from where? Sorry? So any y starts at x squared plus z squared, and then if I go from 0 to 4, I'm going to get like a block. Do you guys see that? I have to have for any arbitrary value of x and z, where does it start? It doesn't start at 0, it starts at the surface, and then goes to the lid. Okay, I like it, maybe. So it goes from x squared plus z squared to 4. And then inside is going to be this thing. So this first step, I'm not going to do anything with it yet. I'm just going to leave it the way it is. Why is this nowhere near as ugly as somebody might think at first? Because this interior is not dependent on y at all. So this integral is remarkably simple, right? You guys, don't let this kind of thing throw you off. Don't give up on it when you look at this. Look at this too. Now, if this was dx, then you go, well, shit. But then maybe change to polar and pray. But let's see. So all this interval on the inside is going to become what? R. Y times that. It's amazing. Because that's a constant. And then I got dA. And it's evaluated between x squared plus z squared and 4. I like it. Let me write that better up here. Take my weird cookie away. Alright, that's not too bad, right? That's pretty straightforward. So I get the integral 4 times this minus x squared plus z squared times this. Now take a minute. Hopefully you guys are sort of with me so far. Try to convert that into polar, considering this is our, well, maybe a little more.
So is the z kind of treated like as if it was the y? Like in a
yeah.
Okay, cool.
Yeah, exactly. Again, because they're dummy variables. So just because I'm in the xz plane, then instead of being x squared plus y squared is r squared, then x squared plus z squared is r squared. Yeah. And what does dA become? Alright. RDR. That's just bad, Jeff. RDR to theta. And of course, theta is going from what to what? 0 to 2 pi 11. And R is going from not -2 to 2, right? Then you're gonna like double sweep that thing. And then double sweep. No. You just got the one thing radar thing going on. And of course, this becomes 4R minus. Yeah, this will be R times R squared, R cubed. And then it's R DRD. Thank you for your patience. I wanted everybody with me. And now that's a beautiful integral. You gotta love that. How much easier. And it's on that same page in the book. I mean, that one you should be able to finish out yourselves, right? I'm not saying every problem in here is going to convert to polar at the end. It's just this problem specifically was easier to handle with polar coordinates. So what do you look for to tell if it's easier? Well, obviously, x squared plus y squared or x squared plus z squared, that's not an automatic thing, but that's definitely like maybe the polar would help me here. So when you look at a problem like, let's see, what's a good one? Oh, okay. Look at number 17 here. Hopefully it's not every single problem, but most of them are going to be a little in your face about what the inner integral should be, which variable the inner integral should be. Is 17 semi-obvious? I mean, what's the input plane going to be for number 17? YZ. Yes. So YZ. Why does it make sense? Because what is x going from to? 4y squared plus z squared up to 4, right? I like it. So then this feels a lot like the one we just did, actually. So that's a really good one. I'll go ahead and try that one, number 17. It's a little bit like what we just did. I would start with some traces, if I were you. Give 17 a try. Yes.
When you're working in like you're using celestial coordinates. Do you use r theta z? Is that correct? Or are we getting into that?
Yeah, we are. Yeah. So it's going to be dz. It's going r dz dr d theta.
No, I mean like if you were to put a point, plot a point.
Oh yeah,
Instead of x,
yeah.
y, z, it would be
R theta z. Exactly. Cool. And I got a little handout with.
r theta 5.
No. It's going to be. We're going to use rho instead of r.
Bro.
Yeah. And actually, it's a point of contention about what exactly to use. There's differences in opinion. Yeah, it gets really heated. No, rho all day. Rho people suck. Oh, this is terrible. Doesn't make it to the news ever, but there are math riots, math demonstrations. Stop.
So it's pretty similar.
Mind over matter. I like that one.
The only difference is the red. The 4y.
Yeah, exactly.
That's really
So I figured this is a good one for you guys to try on your own. Since, yeah. Well, we'll see. We'll see.
the y function to be inside of there.
Oh no, it was given to me.
That was-
This is the problem, yeah.
Okay.
Yeah, just like the x is in there. Yeah. So it's weird. This is the function we're evaluating, and these functions define the region over which we're evaluating this. So it's weird to try to talk about it. So to kind of catch up to you guys a little bit, what's this inner integral's limits? All right. So it's just like that bowl we just did a minute ago. It's got a little bit of a different formula to it. So the inside, now when you integrate this, it is dx and there is an x inside. That's one little difference, but of course you integrate x, you get squared over 2, and then you're going to evaluate that between this and that.
Is it correct to be able to, like, because you know how there's a 4 in the top and there's a 4 in the bottom, limited integration, so could you just pull out the 4 if they're in front? No?
No.
You
No.
can't do 4 times?
No, definitely not. There's no, how do I say this? Because now, you're not, it depends on what the function on the inside does across that volume, for example, for one thing. But also, there's no reason that twice integral a to b would be integral from 2a to 2b. Do you see what I mean? Because whatever the function is on the inside is doing possibly very different things from 2a to 2b as it is doing from a to b. There's no connection there that's guaranteed.
Okay.
Yeah.
If it was squared.
Right.
All right, let me put this thing to rest. So you put a 4 in there, 16, you get 8. Put that stuff in there, and you're going to get, like, pull a 4 out in here. And you get 8. And then y squared plus z squared squared. All right, so what you should get. Yours might look a little bit different, but all you do is pull a 4 out. So make this 4. times this. So when you put it in here, you square 4, 16 divided by 2 is 8, and then you square this, bam. And now I can replace things with my polar coordinates, right? So now it'll go from, so now I can make this dA becomes what? R dr theta. Theta, of course, is going to go from 0 to 2 pi. We really don't have to redraw this out. We just did that one. It's going to be the whole circle there. Now be careful. A little bit of carefulness. But anybody know what R goes from?
0 to 1.
Why 0 to 1?
Because when x equals 4, the radius of that thing is
Yes, I like it. So you want only the inputs that will actually have outputs. So when I get to the point where it's 4, where it's going to be open the widest, then I've got 4x squared plus 4y, 4y squared plus 4z squared equals 4, which is x squared plus z squared equals 1. So in your xz plane, it's just a circle of radius 1 that has all the outputs for this thing. That's the one thing to be careful about. And then you can make this become, yeah, r squared squared r to the 4th. I like it. You get that r, now don't forget about that r. All right, that's exactly the same as the integral we just did, right? Is that cool? If you want to know, I think you get 16 pi over 3 if you do all that at the end. There's no trig function, so you're going to end up with some pi's running around. There's no trig functions to eat those. All right. One more of these that's different, because that was just too much like that one we just did. Let's see if I can get up there.
How's that?
Number 13 there. Oh, I like number 13, yeah. So 13 we'll do all the way out, but you guys try it first. If you have the book, it's on page 1077 in my book. Oh, well, this is still not as bad as it could be. They kind of give it away. Do you see how they give it away? What's going to be the input plane? Totally XY. Say in the region. Now, it doesn't have to be. You could switch the limits if your function just won't work the way they've given it to you.